Okay, so far what we've done, in Module 1, we introduced some important definition and concepts that I need for Module 2 and Module 3. And in Module 2 and 3, we focus on the fluid statics case. Okay. Now, for mechanical engineers, specifically, we are more interested in things that move. Okay. So I'm more interested in how the river flows, different boilers, different cycles, thermodynamic cycles. There's always a flow, right? Or if I'm looking at the solar energy, there's a heat transfer fluid. So it's transferring energy from the panels onto the storage, right? So I need to analyze these things. In order to do that, I may need to look at the fluid kinematics. What kinematics means is basically it deals with the acceleration and velocities that I will obtain. Okay, it will not be focusing on how this flow is generated. That will be the subject of Module 5, Module 6, Module 7, so on and so forth. Okay, and this one I want to set the tone for the rest of the modules. This module is brief, okay, so there's not a lot going on. It's more like to ensure everybody's on the same page. And let's write over here. In statics, this is what we did. We sum up the forces, if you remember, and I call this MA, right? Everybody knows this part. I said this A is equal to 0, so this whole thing, the summation turned out to be 0. Let's analyze your house. Okay, so I have my house over here. Okay, so this is a pretty bad drawing of an house. Maybe if I put over here a door knob, it will be much better. Okay, this is perfect now. Anyways, so what's going on in here is in your house. So think about what's going on. So this is not a statics case. Like right now in this room that I'm recording this, I have the AC on. Okay, there's some cool air coming into the room that I'm in. And also there's an inlet for the air conditioning system, so it pulls up some air into the system, it cools it and blows it back to me, right? Similar to the refrigeration cycle. But here's the thing, the air particles that travel within my house, it will bring its mass, momentum, and energy into the system. And that's how it gets cooled, right? So I said these three things, those three things are important. Mass, momentum, and energy. So I need to analyze these things, okay, for my house as some system or control volume. We'll talk about these definitions, okay? I don't want to get ahead of myself too much. So the first thing I want to talk about, actually, is the reference frame. Many of the books, including the textbook that you're assigned to work for my particular class, is focusing this on a little bit different than me, but that's okay. It's just a different take than what I'm gonna do, okay? Then even the names are the same, but let's look at the Lagrangian reference frame. And this 2 is the Eulerian reference frame. So actually, if you look at the official definition of it, not from the fluid mechanics, but from the physics, here's what it says. Fixed on a particle. Again, now I'm going to focus onto the fluid side, and this particle will be a fluid particle in my flow. Okay, so that's the definition of this reference frame. The Eulerian reference frame definition is fixed at a certain origin outside the flow. Actually, you know, when you read these, or I'm going through this with you, you will may realize that, boy, what is going on over here? It looks complicated. You know this for a long time now, okay? I'm just revisiting these things. So basically, I have let's say that I have something like this, okay? Say bounded flow. So that's like a band. In module 11, we'll talk about and analyze these things, okay? For viscous flow specifically. Anyways, so there's an inlet over here, there's an exit over there. Right now there's a flow, so you can see it's flowing over here. So I have a particle over here, this particle is flowing just like this and leaving my system. Again, I don't want to be giving too much definitions because I didn't cover them yet. So here's what the Lagrangian says. Lagrangian says that, you know what, I'm gonna put my reference frame with the flow. So let's say that I'm using xy as an example, obviously. So this will be stuck to a particular point. And what I'm going to do is there's another point over here, right? All the fluid is made of, infinite number of particles. So it's like looking at this relatively. My origin is moving as well. And if you track this over time, you will see that this is not going to be a function of distance, but it's only going to be a function of time. Okay, so this part is important. So it's only a function of time because I look at my origin, I'm moving with the flow. I'm not jumping from here to here with my origin. Okay, the second definition, convenient and much more what you're used to. Okay, so what I'm going to do is I'm going to call this x, I'm going to call this y. So you know something? My origin is outside of my flow. So now I'm not moving along with my flow. And what is the difference over here is that now if I pick a point, I want to represent this over time, what will happen is this is now a function of time as well as position, you see? Because origin is fixed. I'm not tagging. Okay, that's the definition that we use. I'm not tagging onto the particle. Okay, so that's something that I would like you to know. And I'll give you an example, and here it will be a pretty brute example, but it'll do it. It'll do it. So let me draw this. And I'll ask you, the hardest part about this is actually drawing it. Okay, what am I drawing over here? I hope you see where I'm going with this. Okay, oh yeah, let's put the knob, door knob. There it goes. Okay, let's put the wheels. What is this? This is a one nice bus. Okay, let's put some windows, right? So what's going on over here is, let's say that I have somebody sitting over there. Okay, and I'm gonna call this person B. Let's put a head to it as well. So this person is gonna be B. Okay, and what is happening is there's a person walking, although they're not supposed to. It's moving this way. And I'm gonna call this point C, or rather person C. It's moving. Let's say that speed that I have over here is 1 mile per hour. So this person is moving this way 1 mile per hour, and the bus is going with, let's say, 50 miles per hour as an example. Okay, so the bus is going 50 miles per hour, and this person C is moving 1 mile per hour to the left, and the person B is sitting down. And I have a person outside over here which is waiting in the bus stop. Okay, obviously if the bus is going this fast, it's going to miss it, but well, that's beyond the scope here. So I have a person over here. So my question to you is this: what's the velocity of this guy? You can say this way, you know what? I am this person. I'm sitting right over in the bus, and it seems to me that this guy is coming to me at -1 mile per hour, right? So if I write VC B based on the B point, it's going to be 1 - 1 mile per hour, right? It's simple as that. So the bus speed doesn't really matter. Okay. So now in the second definition, let me look at this way: VCA. Again, my person that I over here, although he or she shouldn't, going this way with 1 mile per hour, fairly slow. And this person is sitting over there. So according to this person, what is the speed of this guy? And that would be 49 miles per hour, because to this guy, the bus is going 50 and this guy is going that way, so it's going to be 49 mile per hour, and it's coming towards this person, right? And that forces that. You see, it's completely different now, right? I'm talking about the same velocity of the same, and this is what's happening over here. This is how I typically teach and relate things. It's a bit different than the book, but that's quite all right. And this VCA is this, okay? And the VCA is basically the Eulerian representation, and sometimes we call this let's call this Eulerian in here, and the other one is -1, right? So in here, that's the material or Lagrangian. This is the Lagrangian description. Okay, so this is the Eulerian, this is the Lagrangian, and you can see obviously this is like the VCB type of. Okay, you're looking relative to each other. One thing important here is that the mathematical expressions that we are aware of, such as the derivatives, are all also defined in the Eulerian reference frame. Okay, So when I have the Lagrangian reference frame, I will get myself something called material derivatives. Okay, and this definition will come in handy fairly soon. Okay, this is the material derivative versus this is the regular derivative that we are all used to, lowercase d, right? That's the what I'm talking about. And I do ask this question when I teach to the students face to face, which one do you think is easier? Except for a person or two, everybody kind of says this is the one that I'm more comfortable with. I want to put my axis over here and see what happens. Okay, and what we're going to do in this particular module, part of this module, not this segment, but this module, is we're going to actually introduce a theorem where it transports the properties from one domain to another. So it will be fairly handy. But at this point, what I want you to know is if I want to express the properties of things with this frame, is actually shorter lengthwise. Okay, and if I'm talking about Eulerian reference frame, things are going to be simpler, but the mathematics will be longer. So it has advantages and disadvantages.